Hi everybody, Greyfeast here. This is kind of a big one. It's one that I've been looking forward to making and posting for quite a while. It's taken a lot of time and a lot of effort to put the simulations together, so I hope you enjoy them. I simulated a couple bodies of our solar system and then a couple new things that don't correspond to anything that we know of yet. But before I get to those, I wanted to talk a little bit about the math that goes into the simulation. So on the screen here you can see that I have Newton's law of gravitation in one dimension, F equals g times mass 1 times mass 2 over r squared. That's pretty straightforward, but when we get to two dimensions it gets a little bit more complicated because we have to work with vectors. On the left hand side of the screen here we have F vector is equal to g m1 m2 over the r modulus squared times r hat. Now r hat is a unit vector, in other words it has a length of 1, and r hat points in the direction that connects the two masses. So for example here we have in Cartesian coordinates x and y, we have the x component added to the y component on the right hand side divided by the square root of x squared plus y squared. Now the square root of x squared plus y squared is the distance between the two masses, and the x component and the y component are the distances between the two masses in both the x and the y direction. Now this can be expanded to three dimensions, and as you can see on the screen we have f equal to gm1 gm2 over x squared plus y squared plus z squared times the unit vector constructed in the same way. We have the x component plus the y component plus the z component over the square root of their squared components. Now that's good for two masses, but what happens if we have multiple masses, more than two? As you can see on the screen here, we've generalized the formula. So now we have F vector I, which is the force, the gravitational force on mass I, is equal to the sum from j equals 1 to n, where j is not equal to I, g m1 times mi times mj over the rij modulus vector squared times the rij hat vector. So what does this mean? This simply means that we take this product of g, mi, and mj over the distance between them squared times the unit vector that connects the two of them. And then we add all of those components up, and that is the total force on the mass I. So for example, if we had three masses, it would be the force on mass 1 would be F1 equals g m1 m2 over r12 modulus squared times r12 hat plus g m1 m3 over r13 modulus squared times the r13 hat vector. And for any larger number you just simply add more and more terms. Okay, so now that we've gotten through most of the math for this video, we're going to move into our first simulation. Now this simulation is a two-scale simulation of the moon orbiting around the Earth. The moon orbits in a very low eccentricity orbit, which means that it's very circular. It's not an ellipse, or not an elongated ellipse. As you can see, the moon is actually fairly large compared to the Earth. They're not very different in size, but the masses are very much different. You can see that the Earth is slowly making a small circle as it moves about in its orbit around the moon. The center of mass of the Earth-Moon system is about 1,700 kilometers below the surface of the Earth. And you can actually see that in the simulation because the center of its circular orbit, about the center of mass, is actually inside of the point that represents the Earth. So I thought that was pretty interesting and pretty convincing. This next simulation is pretty straightforward. We have the sun in the center of the system, and then on the outside orbiting is the moon and the Earth as they orbit about each other. If you look really closely and the resolution is high enough, you should be able to see that they actually do kind of spiral around each other as they move about in their overall circular orbit. Alright, so this is an interesting one. In the center we have the Sun, followed by Mercury, Venus, and Earth, which is about to complete an orbit, then Mars, and then the black line that is an elongated or high eccentricity ellipse is Ceres, followed by Jupiter, Saturn, and then Uranus is in the background, the cyan-colored orbit. Neptune should be coming into view on the right-hand side, and there we go. And then Pluto will be visible on the right-hand side also in just a moment, and there it is. It's a small black line. So in this simulation, there are 6 dwarf planets. Ceres, which I've mentioned already, and then Pluto. Then there is Haumea, Makemake, Eris, and Sedna, and they complete their orbits in that order. So Pluto will be first of those that haven't finished yet, followed by Haumea, Makemake, and then Eris. Sedna, I have already plotted and isn't simulated in this simulation here. The reason for that is that Sedna has an orbit that takes approximately 11,400 years. And Eris, on the other hand, which is the next longest orbit, takes about 590 years, I believe. So if I were to simulate Sedna, it would take just simply forever. So we can see that Pluto is about to finish its first orbit, followed closely by Haumea on the left and in the back, and then Makemake in the top left. And then the only one that hasn't completed an orbit yet is Eris, and that will occur in just a moment. The time scale is not linear in this simulation, and so it speeds up as the further you go out. And just for reference, the orbit of Jupiter, which is the red dot you see in the middle, is 12 years, and you can see it just whizzing by. So I think that's pretty interesting. Alright, so next is the last little bit of math that I'm going to go into, and I'm not going to talk about it too much. But in the next simulation, I wanted to create a circular orbit for a bunch of objects that were in essentially random positions. And so the way to do that is to take the velocity vector is equal to the cross product of the distance vector, or the vector that connects the two objects that are orbiting, times the plane vector. In other words, if you have a flat surface, the plane vector points straight out of it. So if you take the cross product of those two, you can generate a vector that is perpendicular to the displacement vector, which is what I wanted. And it will be in the plane of the orbit that you're trying to create. So using that, I was able to create kind of an interesting simulation, which you can see here, which is essentially a double ring system. I've got 30 randomly placed objects that are in 2 separate planes, and they enter into circular orbits around the central body, and you can see that it forms a double ring system. This probably wouldn't exist in reality, because as the 2 rings cross, the objects would interact and collide, and it would destabilize the system. But it is possible that there could be ring systems that are perhaps not stable, but relatively long-lived, and that could be on different planes, for example. So I thought that was kind of interesting. Okay, so this one here is pretty fun to watch, in my opinion. It's pretty straightforward. I have 25 randomly placed masses that start with random velocities and random masses relative to each other. And essentially I just say go and let all of the gravitational forces between the bodies interact on those bodies. And you can see how they evolve here, so I think that's pretty interesting. And last but not least, we have a simulation of the planet Saturn and its moon Enceladus. Now, you can see Enceladus is orbiting around, and you can see that little black orbits are starting to appear. Enceladus is cryovolcanically active, which means that there's a heat source inside, which causes cryogenic liquids like nitrogen, carbon dioxide, oxygen, so on and so forth, to boil and then to erupt volcanically. So rather than magma spewing forth, these gases do. And as soon as they leave the planet, they freeze into crystals. So as Enceladus orbits, it is spewing all kinds of ice crystals in its orbit. And you can see here that as they shoot out in a semi-random direction, they actually create a ring around Saturn in this simulation. And in fact, in reality, they believe that the very diffuse E ring around Saturn, which is the furthest out that you can't normally see with the telescope, is actually in part created by Enceladus's cryovolcanic activity. So I thought that that was an interesting thing to simulate because you can actually see the creation of a ring system and how it could possibly happen. So I hope that you enjoyed these videos and share them, subscribe. If you have any questions or would like any details, I would be happy to provide them below. Just leave your comments and I'll respond to them. So thank you very much. I hope you enjoyed. Look out for my other videos.